So I know we had a version of that. So it's very similar to the audio NeoPixel code that was zipped there. Let me see if I can grab a copy. It's, of course, buried under yet more layers of things. Let's see. Zip file. All right. NeoPix DB level. Announcement. So I'm going to edit this one. Attachment. Nope, not there from here. Yeah, that. All right. We're going to update that same announcement. So there's now 2 attached to the code you'll need for today. Not even half the students have reviewed it. So that's how I know that it's super duper helpful. All right. Where we are with these is let's see. We've got a couple pieces of the puzzle. I'm going to save this as arrays CPX Neo. X. So this is going to do a couple of things. So I'm going to modify what we're doing here. So it's going to count. We're going to count up and down. So we're going to learn some of the concepts from this, but we're going to sort of blow it up and start over from scratch because as you do, it'll make sense. Okay. Iterate over pins in a sequence. Lights multiple. NeoPixels in sequence, then in reverse. This will use the CPX NeoPixel array. And I could teach you double arraying by arraying the array and then arraying the NeoPixel with the other command, but I'm going to not do that today so as to preserve what remains of your life force. You're welcome. You can thank me in the comment section below. What we're going to focus on is counting up and down in a defined array. So the circuit is going to be the NeoPixels All right, so this set up, and we're going to do a couple. All right, we've got a couple more pieces here. Somebody's got to have some documentation right now. More connection problems. Excellent. Connection problems are always fun and exciting. Okay. Um, so we've got a couple more pieces to the puzzle that we're going to be adding here. So let me jump back over to this. So this is really where the core starts. Um, so they define a timer, and this gives just a range. So this is giving a scope and scale for the timer, and we've got LED pins is the array. So this is an array definition, meaning that we've got the open close uh, break open and close square brackets here. Different from curly braces, square brackets give us the array designation, and that means we've got this process. So 2, 7, 4, 6, 5, and 3 is the starting point for the array for the pins. For our purposes, we're going to reset these. So we can reuse the LED pins, but we're going to cause these to correspond. The array needs to correspond with the array needs to correspond with the new pixel numbers. So that's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, because there are so there are indeed 10. The address starts at 0. So we have to go all the way through 9 to make use of all of these. So these we can't just assign randomly. Those have to be used. The number of pins in this case is pin count. This needs to correspond with the total number of LED pins, so the size of the array. You need that data because reasons. You need to know the size of your total index so that you can get a range and details of what's important. So there's a bunch of pieces of the puzzle that will be helpful. So let's do that. So we've got to set up the elements in the array. So each of these items is an element within the array. Each of these has a physical address, and that's key to the way that arrays work. So yeah, the array elements are numbered from 0 to pin count 1. There's a reason why that's the case. So in the for loop for the pins, they set them to output. In our case, we don't need to do this because on the CPX, the NeoPixels default to output. So for indexing operations where you're doing output, this is an example of a for loop. You're doing an operation over multiple times. So what this is doing, you would have to do with something like an Arduino Uno. You start with this pin equals 0, this pin less than pin count, and then increment. So it starts at 0. It initializes this variable, starts at 0, and counts all the way up to 1 less than this pin, essentially pin count minus 1, by saying as long as this pin is less than total pin count, so it go from 0 to 9 already, is what this is trying to do. It would increment by 1 each time through the loop. So what does it do? It sets the pin mode for LED pins at this pin. This pin changes each time through the loop, and this is where I wanted to be able to show you guys using the debugger, but it doesn't work the way that it should, because of connection issues with servers and things. Might be fixable by the update. I just haven't had a chance to run the update because we have to teach the concepts rather than how to update software. So the LED pins at this pin as the address each time through, set to output. This is what happens for that. So there's a lot of bits and pieces going on there. This is highly, highly important for a whole bunch of reasons. So this is a good example. We're not going to be using this, so I'm going to edit, comment this section because we don't need it. So this is essentially intentionally left empty. We don't need to do those things, but let's see in the comments, what do we need to do in the setup? See if you guys remember correctly. What piece do we need to do in the setup?
Serial dot begin.
For this one, that's a good idea. For the serial, yeah, we can have it. We can have it read back, so it's usually not going to harm things. What else? What else do we need here? We're doing something that requires this.
Maybe.
Go ahead. Go ahead with
Declare
that.
variables there.
We don't need to declare variables because those are up here already. So let's start with this. See if you guys can look through your other programs real quick and find it. There's another piece we need to do there. So let's start there.
Does it include libraries?
All right, we've got a few things that we still have to do here. So you're getting closer with that question. Um, in order to use the neopixels, what do we have to be able to do? Seems like everybody's forgotten.
Do we have to set the pin mode?
Nope, not quite. We don't have to set the pin mode.
Is it
One
the
of them.
circuit library? You have to initialize that.
Yes. So we need these two includes before we even initialize the variables. We need the includes, and then we need to do what after that? Does that jog your memory any?
Had it in the setup too.
Yeah, it's got to be in the setup. So it's got to look like this, right? Circuit playground.begin, so that we can call on those functions and make use of them. Okay. So those are going to make a big deal about how these are all going to work. That's a major, major, major function. So we've got a couple pieces that we need to make run. These are things that are going to be necessary for leveraging those functions, including both as just a more of a safety measure. The pin count, I think I'm going to come back and use because this is going to be kind of an indexing variable, but sort of. It's a reference point. There's ways that you could automate the sort of, there's functions you can call on, or you can write a function, but we'll get to function writing later. There's functions you can call on to give you the length and size of things. Certainly we'll use this a lot in MATLAB. So this concept of arrays is something we're going to be using a lot. Each of these numbers has an address, and the address is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So each of those positions in the array has a number. That address in the array has to be what's called indexed, meaning you run a loop to do an operation on an array. Almost always when you're storing data, and we'll talk about trying to set up moving averages and reference frames and things later, but I want to make sure you guys understand what an array is and how it works first, and then we'll move to some of the more complex stuff, because it's really, really critically important to understand the fundamentals for arrays. So in the loop, the first thing that they do is they start, they set up an integer. They use this pin as what's called the index variable. So instead of I or X or N or something like that, like we've used previously, they're starting an integer, this pin, at 0. And they're saying, as long as this pin is less than pin count. So we've set pin count up here. Increment this pin, so plus plus. So for index variable condition increment type is what the for loop, that's the 3 inputs that function needs, all separated by the semicolons because everything's semicolons. Digital write this pin to high. So in our case, the command is going to be a little bit different. Does anybody remember what we used previously for actually assigning the for actually doing the count? So delay and then timer. This is another valid use. You can put in a variable that is also an integer into the delay function, and you can update one line. So this is another programming efficiency thing. Define a variable for something you're going to use a lot, like delays. In the case of something like this array, where we have to have people actually reading and observing and understanding what's going on, because the code on the hardware can execute much, much faster than we can actually perceive what's going on. And I know that some of you think you can 360 no scope with like single digit millisecond precision, but the human body can't actually activate all of the chemical cascade sequences to react that fast. So you're not quite there where you think you are. Not a guess. So instead of digital write to LED pins and this pin address each time through the for loop, so this increments by 1 and setting it to high, then a delay, then setting that to low. We have a similar process, but what does that actually look like for the Circuit Playground Express?
Isn't it like set NeoPixel color?
Yes. So Circuit Playground set NeoPixel color, and remember we need a couple pieces of information. Specifically, that function is looking for 4 of them. So Circuit Playground dot set pixel color index variable, red value, green value, blue value. And that's what's going to give us the range that we need here to be able to work with. So Circuit Playground set pixel color. We're using this pin because this is a helpful index. So long as this pin is less than pin count, set it to, and we could do, let's see. I used to know this because reasons. I need the RGB values. Okay. Here we go. So it's in the branding guide, teaching you guys the important things. So 95, 37, 159. You'll find out later. Okay. That'll be your next mission, is in the comments when you figure out why this specific set of RGB values, when you know, you'll know. And then you have a couple different options. You need to turn the pin on, leave it on, turn the pin off. So you have a couple options. You can set pixel color, or you can turn them all off. In this case, you want to set this. The simplest way to think of it is turning it back to 0, 0, 0, because that will turn off all of the individual values. Then it will step out of this loop. So once it's completed this, it'll step back up and check. It'll add 1 to this pin. It'll say, okay, this pin is 0, run through. This pin is 1, run through. This pin is 2, etc., all the way up until 9, and it'll run through. That will set all of these values. So the index, or actually I misspoke earlier. I'm going to clarify the positioning. In arrays, the initial position is 0. The end position is total array length minus 1. So in this case, 10 total values minus 1. So our numbers and position assignments are the same for this. I wanted to do that to keep it simple. That's why I'm using the NeoPixels, and that's why I'm converting starting from this file. There is a purpose behind the madness. Trust me. Okay, so this why semicolon there? Never have I ever. Okay. Yeah, no extra semicolons to confuse things. Actually, no, does need a semicolon. Because does need a semicolon because it will throw a compiler error if you don't. Yeah, so actually must terminate in semicolon. Otherwise, you will get compiler errors. Yeah, very important. Okay, set pixel color. So loop from the lowest to the highest. Then, so 100 milliseconds in between each one. Then for this one, you're going to do another step. You're going to do this pin equals pin count minus 1. You have to do this because you need to start at position 9. So pin count is array size, or in this case, array length. It's not technically array size. Size is, in this case, for the array, 1 row, 10 columns. So it's a 110 size. Length, meaning total number of characters in the array, is 10. We will use length and size extensively in MATLAB because between length and size lie most of the problems with your red love letters. That's called foreshadowing. It's basically like a cinema picture around here. Things to come. This pin equals pin count minus 1 because the assignments need to match the numbers that are set up in our array. That's not always going to be the case. This is just a really good learning example. This pin, so long as this pin is greater than or equal to 0, meaning rather than just greater than, you just did this, it would not activate the last value because 0 is a valid value, whereas up here in this array, 10 is not a valid value, so we don't do greater than or equal to. Here we have to do less than or greater than or equal to. Here we do not do less than or equal to because reasons. But we also have to decrement the pin. this index variable. So decrement meaning decrease by 1 each time through the cycle. Same thing. Delay timer. Only in this case, we're using the exact same code with the exact same index, because the index in this one goes the opposite direction. Okay, so both of those for loops happen inside the loop itself, and that's it. So this is actually a brutally simple program, even though not exactly. So Tom Igo, I think he's done a few of the example libraries. I don't remember his original. All right. So I'm going to make sure we're compiling for the Circuit Playground Express. Verify. This should verify flawlessly. But I didn't specify the 9600 baud default because I'm only on second coffee today, and that is a very poor life choice. I should be on like 8th coffee by today at this point. Okay, so there's that 12 and 14% of dynamic memory. This time it's not screaming from the rooftops. So we're going to upload this and see what the NeoPixels do. Counts up and down. So this is also very common. This is the code also known to be the operation of something called the Larson scanner. I'm one of probably 10 people on the internet that actually know what a Larson scanner is, so I'll ask the question anyway. Anybody familiar with what a Larson scanner is?
No idea.
Bueller, anyone? It's only the greatest thing ever devised by man. The scanning back and forth LEDs used to be in lots of very high-end expensive car alarms. Car alarms are things that we used to install in cars back before all of the manufacturers converted to some sort of RFID type system, and proximity keys and all of the things that you guys have grown up with, and you're just like, what, you actually had to like install a car alarm? Yeah, for hundreds of years, going all the way back to the horseless carriage, there was no such thing as a car alarm. It was called a dog. Okay, you don't know what the Larson scanner is, so I will have to clarify, because it's only the most important thing you need to know. Let's see. Yeah, here we go. So I will share this. In just a second. And then it will all become clear. It will all become clear. Yeah. There we go.
Knight Rider, a shadowy flight into the dangerous world of a man who does not exist. Michael Knight, a young loner on a crusade to champion the cause of the innocent, the helpless, the powerless, in the world of criminals who operate above the law.
There have been some advances in aerodynamics since then, and it turns out if you try and drive a car 300 miles an hour with all of that fiberglass nonsense sticking off of it, it doesn't go very far at all, and it will in fact not reach those sorts of speeds. So that is the Larson scanner, and now you know. So that is the code that operates in order to cause it to scan back and forth. Now, in his case, he was doing that by relays with bulbs when that was created, but there were a few examples where that was not used in the same way. So, has anyone figured out why we needed those particular values in the RGB?
Is it because it's purple, like GCU?
Yes, that is the officially sanctioned brand guide RGB values to GCU, because that's a thing that you guys need to know as GCU students. So because you purple all the things at GCU, and that's how you do, that's the values. Now, one could argue, looking at that that doesn't really seem to be exactly the deep purple that you have come to know and love so well, but yeah, that's what filters are for on Instagram, right? Make you look like something you're not actually. Welcome to real life. All right, so in the arrays, now we need to do a little bit more with the way that these work. So this gets you familiar with how to actually use an array. So I've kind of tricked you in that we've done this before. However, we haven't actually used arrays like this before. Okay, so also, in case any of you guys wanted to know why Elon Musk is the way that he is and why he wants a car that goes plaid, which is also another reference to perhaps the single greatest cinema creation of all time. Bonus points if you can name where that reference comes from. Knight Rider is a core part of why Elon Musk is the way that he is, and why the plaid has a steering wheel that is cut off. It's because of Knight Rider. So these are all very culturally relevant things, even though you think I'm just some washed out revision of 80s history. So things that are helpful to know. The Circuit Playground can do some other things with these. This gives you at least a starting value. So there's a lot of different things that you can do. You can count them up based on a sensor reading. So that's going to be the next iteration that we'll do for this. Any suggestions on how we would approach doing that? how would we approach taking our sound input level?
I think you'd have to use like if statements. So you specify like if the sensor is outputting some sort of range, and then you set the pixel color or pixel number to something.
Good. Correct. So you need some sort of comparator operating in the code. This is just fundamental to everything that we do. So we have some of that. So we need another variable, and we can do in this loop, we're going to need something like this, right? Start a definition. Circuit playground mic sound pressure level. And this specific function, 30 worked okay for us. We found that we needed an empirical correction factor from our code. Then we can begin, and we can say something like, if the sound pressure level, so we're going to need something like this, if the sound pressure level is below 60, or is there another way that we could do this? So we've got a couple options on how we can set up the logic. We can run a couple of these. So the way we did it last time was an if, else if, else case. So we can still use a structure like that, but there's a couple modifications that need to happen. Okay. So if sound less than 60, else if sound is less than 75, anything that is, so this takes care of the boundaries below 60. This one becomes 60 to 75. This is anything above that is the else case. So that's the way this logic is set up to capture things. What variable do we actually need to change in order to have control over what the sound level is reading? I'll give you a hint. It has to do with our for loop. See, I could do like the Ukrainian mathematician that taught one of my classes, where he would write the fundamental equation on the board, then he would write the final answer in equation form, he would skip all of the steps in the middle, and he would simply say, the derivation is trivial. I could do that. And then you guys would all look around at each other and think, oh God, we're all going to die. But I would much rather you take some level of participation in at least thinking through what your approach might be. What would you update within that logic? What variable would you have to change?
Well, is it this pin that we have to change? I guess if we want them to like sequentially light up, or if they just depending on how we want them to light up, we have to change it instead of like sequentially going up one by one, unless we do like 100 else ifs.
Correct. So in this case, you would set a range. So there's a simple way to do this. So if sound is less than 60, so that's the quiet case, we would say this pin is equal to 3. Next level, else if sound less than 75, so next stage, this pin equal to 6. Else, meaning the case where it's over that 75 range, this pin equal 9. Then, depending on which comparison, right? So we have to have a variable sound for this. So we're defining in the loop that sound is this. But it's really proper practice to include up here before we get too carried away. Allow the sound to store decimal values. We're treating it in integer ranges. That's okay. That's still allowable. There's no illegal procedure with a 200-yard penalty in there. So the next piece of it becomes, let's see. So if this pin this is our comparator to give this pin a range based on the sound input level. So now we've got what we need to be able to verify that this is still reasonable. And the key that we come up against is we're going to at the end of each loop, that's what we're going to have to do. At the end of each loop, this is a hole in the logic that is going to be problematic. Here. Better strategy. We're going to use pin count here. Because this is an array length variable, and that's how we've defined it up above, pin count. So we initialize pin count at 10. We're going to redefine it down here as needed. And this is going to reset the value each time. At the very end of each loop, in order to make sure it goes down, we should reset pin count equal to 0 because reasons. So inside the loop, that will reset the pin count to 0. It'll take a new measurement. Based on that, it'll give pin count a new assignment. And if suddenly the universe went soundless, this would account for that case. So it's still going to fall under this range, but this will reassign pin count to 3. All right. That works. That works. All the pieces. This will all make sense in a second. Yeah. Too much memory. Too much memory. Oh no, we're all gonna die. No, it's fine. It's 15% and you're out of memory stored space. No, wrong. Need a soundboard with certain sound values. Okay, pin count. All right, so this compiles correctly. We're going to re-upload it. So it's going to count up and down based on the sound pressure level. If it goes up, it's going to count higher and higher and higher until it gets really loud, until it gets really loud, really, really loud. And then it will go all the way to the top. And then when it's quiet, it'll go back down. So that is how you change the values in order to pick up more noise and a higher threshold. Son of a gun, it's going to need to go all the way to 10. Maybe we should try 11 just for funsies. Turn it up to 11. Nope, fail. All right. So I'll have to keep working on that. Probably also a reference that you guys are not familiar with. Okay. Good. So it compiled. Why it thinks the memory storage is full. Utterly beyond me. Go equal 10. Because reasons. I'm going to reflash this again. Because I want sound to go up to 11. And it can reach all the way to the top, can reach the last pixel, but you have to include one more than the index variable because reasons. No, it's not going to do it. Okay. So you can use that to determine the sound pressure level. The next graduation from this is to go up one higher. There's also a couple other things that you can do that are interesting here. But we can store the data in. It's easier to store data into an array from a light sensor, really, because your volume and variability of data is a little bit more radical than the audio environment. Unless, of course, you're listening to my favorite category of music, in which case you don't actually understand any of the words that are happening. So there's that. So there's not really a lot of information. Yeah. So let's see what are, there's one other file I'm going to need. Light sensor. Is it light sensor? Is that the one I'm thinking of? There's a couple that are very interesting. Mm, 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 mm. This one doesn't do. Yes. Yes, it does. This one stores to an output. Yes, this one stores to an output. There's a couple options. There's a simple way to take an average reading frame, and because of the level of complexity of this, I might move one of the things. Let me see what the next yeah, serial monitor. There's another reading frame of reference. And then we turn around and get into libraries and functions. Yeah, so we're building up to some of the stuff that we're actually going to be trying to reach mastery of in week 8, even though it's only week 6, because all of this has to build on each other. Yeah, I'm trying not to have to teach you guys like an extra 12 levels of things all at the same time because reasons. Question.
Yeah, how hard is it to get these to like stay on instead of like sequentially oscillating?
Not hard. So, 2 steps in that are, there we go. There's the arrays. So one of those steps is this. where you go to edit, comment that out, and // to these. Then at the end, you do this and say Circuit Playground Express. No, you need I need that like Trump soundbite. Wrong. You need this piece. Based on the value of this pin, you then need to go through and turn them all off. Or at the end, use the turn off the NeoPixels command. Yeah. Yeah. This is the simple way to do that, because you then count back down and turn them off at the end. If you wanted them to just stay on and not come on at all, or not turn off at all and only turn on some of them, you would leave this commented. What that behavior is going to do is it's going to upload. It's going to leave the first 3 lit up until you reach maximum potential, and then it's going to stay. So the problem with this code is this will turn it all on, but if you want them to then turn back off and measure and stay full each time, to control that, you have to pass through each run of the loop. You have to turn the pixels off again. There is the simple command to turn them all off, but it's not in this group. Yeah, I don't have it in this one either. Okay. So there's a couple pieces that we'll need for the next step. Yeah, this is a good example of how to work. At least an example of how to work within a given reading frame. So I'm going to share this example. Yeah, light sensor input. Okay. So light sensor is analog pin A, 8. This data sheet gives us a saturation at about 4.6 volts, and that is about 1,000 lux per volt per the data sheet graphs. Remember, we talked about that a little bit. So this is still the approximate data sheet. We're going to include math.h, which is a math library. Couple reasons why we want to be able to do that. We want to be able to do things like take an average of some of the data, and you guys have seen some examples of this, but we're going to include some more specifically here because that'll be helpful. You're initializing the variable for the photo pin, so that's at A8. Um, the voltage value from the sensor is what we're using this as a basis. So we're going to read in what that value is, and the scale at the low end, it brings in about 2.3 volts at the low end. Again, based on values from the data sheet. So assuming it's working correctly, we're going to use V0 as a float. So there's decimal. Lux is an output variable. This is essentially your X value. Then we're going to calculate from Y equals MX plus B. We're going to use a float variable of M. We're going to pre-allocate an array size to be 100 values. We're going to call that L, and this is an array of integers. So 100. And you'll note the comment shows up now in this. Again, things that didn't used to happen, but now does, making your life so much easier, so that when you're down here using L, it shows you what this is supposed to be doing and gives you information about the size of the array. So L 100 pre-allocate some memory to help compile things a little bit more efficiently. Sum equals 0. So this is another variable we're going to be using. So in our setup, this is where we're hiring our variables and telling them their jobs. So serial.begin. This one is another operator that we haven't used a lot, but this is a while not serial. This is a command that basically tells it to wait for a second, just chill out for a second while there's no serial data. We've seen some examples where we connect to the serial monitor and all of a sudden it's all the way on step 2 or 3 or something. So it chills out the board until serial communication is established, then sets up the photo pin as input. In our loop, we're going to set up a for loop with an index variable, in this case I equals 0 for I less than 20. So the range for I technically is actually 99. So this we're going to do less than 100. Because we're using some of the information within this, there's actually there's still 100 total characters, but it starts from 0. So this will fill the L array completely. V0 is analog read of the photo pin. So the millivolt reading comes back in. We didn't talk about this extensively, but that's essentially what the values are. So we rescale the 4.5 to 2.3 range to 4,000 minus 2,000. Again, values that are based on the data sheet. So that gives us a slope from the data sheet. This is values that are pulled 4,000 lux versus 2,000 lux at 4.5 versus 2.3 volts, meaning 2,300 millivolts versus 4,500 millivolts. Rescaling everything. Now, map, super helpful function. We haven't really talked about it in this case. It does not mean manifold air pressure. It actually means it is a defined function. What this does is this rescales the reading our input from the A to D converter, meaning the analog to digital converter, to actually read in millivolts. So as a test, we can write V0 is, and then the value for V0, and then lux is this. So I'm going to uncomment these so that you can see what the output values actually look like, and then delay 10 milliseconds in between readings, because you want this data to come through at a pretty reasonable rate. And then you have a for loop. So this is one of the ways to do an average. For loop for a value of the first 10 that it captures in that string, increment the sum. Plus equals means you add together all of these things. So this is a shorthand. Add together L at position I index variable. So add together the first 10 values. Sum equals sum divided by 10 to give you a manual average. You can do an average calculation, but you need to have the array together. So sum, every time it runs through, you're adding the next value to sum. So sum is greater each time through the loop, and that's the way that it indexes. So there's a few different things going on. We're going to verify this. Of course, it's fine. It was, after all, authored by Darth Vader, so he knows a thing or two about programming. So we upload, check our serial monitor, and we're ripping along with data. I'm going to drop that delay to a much more human readable number. So that's a lot more reasonable. Illumination levels, we can see how they change. Millivolt reading is rescaled. So we can see what the lux values are versus the output voltage. So the map helps us to rescale a couple things proportional to a correction factor. So it's very analogous to what we've done in some other examples. And then we can sum is and sum. We re-upload this. We will get a printout of what's going on. So it's running through, printing out a bunch of these because of where and how the printouts are. It's giving you live examples, and then the sum is only occasionally showing up. So that gives you an average every time it runs through 100 data points. So that's one mechanism for being able to take an average out of a data set and store it into an array, is by saying, here's the variable v0 is what we're actually reading to. We then remap it based on the scale from 0 to 1023 becomes from 0 to 4600. So this rescales voltage to lux values proportional to M, which is the slope, and lux are voltage divided by 1000. So that divided by the slope gets corrected, and that value gets stored to I. So V0 gets remapped, and that's why V0, if we wanted to know what the actual read was in millivolts, not the remapped V0 to lux, these would have to move up above the M, and that gives us when it's done uploading, that gives us what our V0 is, and we can actually see that V0 and the lux values are different. So as soon as we increase that by having it closer to an illumination source, we can see what's going on there, and we see the average change. All right. So questions so far on arrays? Let's do a grand clarity scale check and see, is this making sense? Or have we completely departured into a foreign land and language? I'm trying to do this in small sequential steps so that you guys aren't simply being drowned in all that there is to know about programming all at the same time. Are you guys starting to be able to make more sense of what the code structure is doing? Is it becoming more obvious what some of the things are trying to do? I'm hoping so. All right. So map's very useful function. It's one of my favorites. Gives us some pretty good ideas on what to do. I'm gonna go ahead and save and update that because that's not a terrible example. One of the only other things is the moving reading frame. There can be some examples of those that can be very, very tricky. So let me see if I can find it. Hmm. Uh, where would this be? Mm. There's a couple. Where is it? That's the next question. If I can find the right file, I can quickly walk you through an example of open reading frame code. However, that is not going to be a simple one to explain. Hmm. No, it's not there. It's not there. It's not there. Okay. So I will have to go poking around to find where this goes. Yeah. Maybe it's here. Yeah, this looks closer. So there's another array example, but not the one I'm looking for. There's one more that has a couple really good keys. Mm, no, there's one more. Um, yeah, there's a couple others. I'll have to dig around a little bit to find it because there's a couple good examples with a uh, it's a customizable reading frame that runs over the top of your loop and grabs a running average from your data window of a customizable number of data points. Showing you an example like that rather than walking through all of the individual steps to make that happen is so much more work. Yeah, that. Um, I'll have to find it. 'Cause I don't think it's this one under light sensor input. Nope. So that's the one that we're using as a reference. I thought that was what it was originally, but yeah, I don't use a reading frame in that one either. I'll have to go back and find that one. Oh, it's this one. It's this one. Okay. Yeah. This is the one. So I'll walk you through kind of what this actually does as our sort of last piece of today. Always so much to do. Start with including the libraries, defining two variables, the bin and the frames, total number of open reading frames that are fast Fourier transforms that are averaged together. Start the circuit playground so that you can access the commands, and then serial begin, and your setup is complete. In the loop, you set up two different kinds of variables. In this case, you're specifying unsigned, meaning no positive or negative association there, just integer 8-bit I and j. So this is how you define two variables at once, I comma j. So all of the values that you're going to use, you can use commas and set up a bunch of variables all in one line. We haven't done that yet because we haven't had code that's been that complicated to start needing them, but I knew we needed to start doing some work with arrays before we started using these. So the 16-bit unsigned integer allocates more memory for the values to the spectrum array and then the average. So the spectrum is the total output of the frame buffer. The reason we're using frames and bins and terms like buffer is this is actually what the real hardware does in real life, not just in our sort of half pretend code. The average of bins gives us some more information. So there's a couple ways to think about this. So for index variable j, sometimes if you have multiple for loops, it helps to have some values. This one is set up to throw an so this one, this is what's called a nested for loop. So for loop inside of for loop. You can't use the same index variable I both inside a for loop and a nested for loop because it'll get confused. So you have to have additional variables. So it's not uncommon to have a triple nested for loop. Again, this is why we didn't do this a few weeks ago, because just too many levels of things. When I was babbling about open reading frames and frame buffers and things, it sounded like gibberish, but this is why. So you have a for loop, you have a main for loop that is this one. From here to here, there's our curly brace sandwich. J is the index variable for up to frames. Frames being 4 total frames, 4 total cycles to be averaged of the bins where the data is actually being stored. Think of it as a plastic bin that we're dropping all of the data into, or filling up almost like a faucet into a bin. It's a good way to think of it. So this internal for loop is indexed with I, for I is 1 to less than bins, increment I. Spectrum, if spectrum, which is the data array, spectrums at position I is greater than 255. Spectrum I equals 255. This limits outlier data. The Circuit Playground Express got a electrostatic shock while it was trying to do that specific line in memory or something. Some value is off of 255. This contains and constrains variables, and how much of what can go where. This resets 255 as the high limit, and if I is comparable to 0, then take the average of I at spectrum position I. Otherwise, take the average of I at position of at average of I plus spectrum of I. So the Circuit Playground is listening and doing a fast Fourier transform. So it's trying to pick up what data it's gathering. Then we take an average in the bins. We do an average divided by frames to rescale the average to an actual true average. So divide by the total number of values that are being used. So if you're using 4 frames to pull each case, 30 some data points out of the background of hundreds for each frame, 4 frames, that average of averages is what you're doing here. So it's dividing the number of the average by the number of averaged values, by the number of averages of those values, not by the total number of averaged values, to be less unclear there. Your max value is another, and max index are another couple variables. For I 0 to less than bins, incrementing if the average is greater than max value, which equals 0, reassign max value to the average of that location. And then max index is I each time through. So you update those can become useful things later, because we can print the actual max value and then serial print the max value. You can print the index of max value, then serial print line the actual value. So what this does, let's compile and upload. Status 1. Recompile. No. With the language reference, you should have that. Oh, maybe that library set doesn't include the fast Fourier transform. All right, so this is another reason why I wasn't going to use this example a couple of weeks ago, is I wasn't 100% certain that the FFT variation was going to come through correctly. I'll have to track down which library that set shows up under, because that will create some additional confusion. But that's where our limitation is in 293 under that function. Yeah, there's a way to address this. Because the FFT, yeah, the FFT has an issue. I think that's supposed to be in that library, but I'll have to go back and look and see. I may have a version of the library where the FFT version is not defined, and that would create that particular kind of error. And I don't remember if you can just replace this with Mike Listen, because it might have to be spectrum equals circuitplayground.mike.listen. There's another couple variations, and I think they've been updated, so I don't know that this one's a current example, but it does give you some examples of the reading frame and how these are implemented. So this turns out to be useful for a number of reasons. Yeah. All right. So we'll have to come back to see whether or not we can make use of the fast Fourier transforms. All right. You guys have certainly reached the mushy oatmeal stage. So I'm going to end it here and ask for any questions that you guys might have. And if there's no questions, then we will reconvene next week.